Okay. Yeah, thanks for having us, first of all, and thanks for coming to our talk on the last day, at the last slot. So I know everybody's tired. We're going to try not to make it too boring.
I'm just going to say test, test, test. That works?
Yeah.
Yeah, great.
Okay, then.
Yeah, then
let's start.
Let me start. Hi. Thanks for having us. I'm actually really excited to give this talk to you. First of all, it's been a while since I've been here. This room has changed a lot. So great work, Michael, everybody who was involved. It looks great. And so many new faces. So just for me to get an impression, raise your hands. Who is actually from the University of Bremen? Okay. Who is external? Okay, some. Who is a PhD student? Okay, a lot. Who's before PhD? Great. And then the rest after. Cool. Then I know. And I guess everybody's working with robots or with decision making. Today, Alexis and me, we want to talk a bit about our company, what we're doing, Ubica Robotics. Let's say at a rather high level. So it's going to start with a really boring, presentation of the product, of the company, how we got here. But I think it's going to be fruitful for context for those of you who do not know us at all, and for those who know us, maybe what happened in between. And then we wanted to make two technology spotlights, which came up when we took the technology that we had developed here in EASE at the uni and tried to make a product that works on a bigger scale, with more people and continuous operations, which I think are both very interesting. And you probably have heard about them, but then once you start to apply these technologies, you get into nitty-gritty details. And we wanted to spotlight them a bit because maybe some of that is also interesting for future infrastructure, future work in your labs with robots. Okay, so we're going to switch in between, first the boring company stuff, then the technology stuff, and we're really trying to make it 50-50, such that it doesn't get too draggy. So, yes, we're Ubica, and we are making autonomous scanning robots. Oh yeah, the slides are gonna mix in language. We copy-pasted that together, but I think I looked at it, we're gonna manage just with the English explanations. So we're doing scanning robots that drive through retail stores at night after everybody has left, and that take pictures of the shelves with a lot of cameras which are mounted on a static axis of the robot. Robot also brings light because typically the light is off in the stores at night. This was, it was still on for this promo shot. And then we're running all types of software to detect what was seen in the images. And it's basically focused on all the furniture and all the inventory right now, right? So the robot, while it's driving, has to detect, okay, here's a shelf, this is where it starts, this is where it ends, this is how deep it is, this is how high it is, the width, but then also where are the shelf layers, what type of layer is this? Is this a mirror? Is this something with a basket? What's on the shelf in terms of price labels, what's printed there? Do you have some promotional stuff here? Do you have some wooden installations? And then we go and actually look into the shelves in terms of the products. Are there products? Is there empty volume there? Is there the right product relative to the price label? And so on and so on. And all of these individual detections, they basically get collected and made sense of, and together with the localization of the robot and so on, to yield a data structure which we still call the digital twin. You heard something about the digital twin in more general, a taxonomy this week I've heard. So yes, that's basically what we then ship to the customer. So actually we have two products. We have the real physical product, which is the robot, and we have the digital product, which is the digital twin, which gets delivered every night for every store. And in a sense, the customer is not interested in the robot because the robot is just the measuring device. So the robot is just the source of pain. What they want is the data. So if they could get the data without the robot, then they would be sold, but that's right now not the case. But so you have to look at the company as selling two products that go together. But let's focus more on the one that's interesting for now. Here we have the results of parts of the results of one scan of one of our customers. This is a DM store. I don't even know which one. It's basically showing you the registered point cloud. And I use this image, this animation a lot to explain to people what the digital twin for us is, especially new applicants use this. So the digital twin is something that you can load in a rendering engine, like in a game, in a computer game, and then you can walk through it. And you can look at it, and it's going to make sense to you as a human, meaning everything that in reality has a 90-degree angle will have a 90-degree angle in here. Everything that's a meter in reality will look like a meter in this world. Everything that is an individual product with colors will be the same here. But actually, that is not what we're selling. What we're selling is that the digital twin is an information processing let's say, instance. It's a database. It's something that you can ask queries to, and the answers to these queries is what actually makes the money for the retailers. And so I brought 4 queries here, which stand for different stakeholders that are interested in this twin. And this is supposed to show you how wide the range of applications is. So the number one is, what is the shortest path for a given click and collect order, which is something that got more popular with our customers, that their customers, you and me, we shop online, and we say, I want to pick this up in an hour in a store, and then a clerk has to go and pick the object. And that is actually a new process for, let's say, retailers. If you go back, the original idea of the supermarket, the patent from the 50s, was that you and me, we pick the objects from the shelves. That was the innovation based on the mom and pop store, where you go to a counter and you say, oh, I want 500 grams of butter, and then I want some cheese, and So the supermarket said, we do the picking. Now they have to do the picking again. But they're not prepared for that, because the basic task that they have is they put the products into the shelves, they help at the cashier, they maybe talk to you, recommend some products. But order picking is a new process, so to speak. So the idea is, let's give the clerks a smartphone that helps them go to the store, find products quickly, because some of the clerks will be really good at this, some will be bad, because maybe they're new, whatever. So you want to save time. That's the use case. On the top right, we have something very different. This is asking, where are the products from Ferrero placed in that store? Ferrero being a famous chocolate producer from Italy. Which highlights a thing that a lot of retailers do, is that they offer against discounts preferential placements to the manufacturers. So let's say Ferrero only gets placed at eyesight next to the cashier where it sells better. So as soon as you have such a contract, of course, you get the question of contract compliance. You have to check it. State of the art right now is that this is done manual. So the manufacturers, they get the right to randomly go to a store of the company that they have a contract with, take pictures with people who then annotate by hand and check, right? And so this is like individual checks, right? You cannot do this whole scale, and it costs money. If you have a measurement device like the robot that uploads high fidelity data, you can do all of that compliance checks in a cloud. Third different type of query is this maybe more interesting for the operations of the store, management on how people work. It's like, where do I have an out-of-shelf situation in the perfume section? That is kind of highlighting a situation where maybe the store manager comes in the morning, has a lot of goods to replenish, but then people are sick and you only have a few clerks on site, and you have to decide, what do I actually now put into the shelves? And maybe now you want to focus on the products that are really missing on the shop floor, but you have them in storage, and you want to get to those first, but actually you want to start with those where you make a lot of money, right? Where the margin is high. So that could be the perfume section. Yet another question is what you and me would maybe ask when we're shopping in a store, where we're asking, where do I find the organic hummus in this store? Because maybe I'm new in the store, I don't know the layout, or maybe I know the store, but this is a new product that I'm buying because found it in some recipe. Now, the idea is that the retailers, they take this data, they package it in this customer app that you can download, and then it has a product finder with in-store navigation, localization that helps you shop. Now, granted, this is something that not a lot of people will do, right? A lot of people probably are not into tech-based shopping, but some are. And for those people, the retailers want to appear more attractive. They want to offer that service. So this is basically 4 totally different types of people who want to know how the store looks inside. And right now, in Germany, I would say almost all retailers, they can answer these questions, but only the experienced clerks on site. There's no computer system that can answer these queries, right? And the idea is that if you have a measurement device like the robot delivering digital twins every day, you can have IT systems answer these questions. And you can then expose those to people through smartphones or expose those to all types of automatic processes like buying new products, planning routes for picking, for replenishment, etc., etc. So that's the proposition. I'm gonna jump over this quickly because I took too long just to have said it. We are targeting big chains. So basically companies that have products on shelves that sell a lot, because selling a lot in one day means the shelf changes a lot, meaning there is a need actually to re-perceive the state of the shelves every day. And retailers that have a lot of stores, because even though we're aiming for a generic solution, you need to have, let's say, an initial engineering project. Those customers, they need different sensor setups. For instance, we do a lot with Rewe, they just have shelves, with DM, they just have shelves. We also do a lot with Rewe, they have freezers with pizza inside. To see inside of those, you need cameras that look at an angle. They don't make any sense at DM. So these different types of customers, they need different sensor setups. So we have an initial engineering project of redesigning at least the sensor axis. Then, of course, you need to adjust the software based on what the customers want to see. So all of this to say there is an initial engineering project, and that has to pay for itself. And that is only possible if you sell a lot of robots. So big chains, standardized, fast selling products is what we're going for. And just to have said it, there's competing technology. Might actually be something to think about. That's actually interesting. Of course, other robots, but the bigger thingies are cameras on shelves, cameras in the ceilings, smartphone-based solutions where people take the pictures and you just acquire differently, intelligent shelves with sensors built inside. The main story is the mobile robot has two advantages and some disadvantages. Number one is it's very flexible. The store can change layout, can move shelves, can put shelves in the aisles. The robot will react. It will just drive differently, position itself differently to take the pictures. If you have fixed cameras, any types of layout change is a bigger construction problem. And the second one is the robot just scales better with bigger stores, because you basically have a fixed relationship between the amount of shelves, cameras you need per shelf. So let's say a DM is hard because they only have few shelves. A Kaufland is enormously expensive to equip with a lot of cameras. And here, the robot, because it's cameras on wheels, is just cheaper. Okay. Yeah, this is just a happy slide saying, hey, we were successful. I'm going to jump over that for time's sake. And then Alexis takes on the next part where he's talking a little bit about, okay, how did we get here actually from the uni? This is like part of an old talk,
yeah.
But we thought it would be interesting for you.
Thanks. Genau, so basically, I like this picture because it's in a garage, and that's where all startups start, according to myth. But we started here on 2 rooms in the second floor. So it didn't exactly look like this, but we had a talk about this, I think, in a fall school 2 years ago. And I'm just going to go over it a bit so that we discuss a bit of the main things. And coming out of the uni, we think it could be interesting for you. So it's basically this concept of taking something that gets developed at the university as part of your research, and you want to turn it into a company. So what do you need? How does this actually work? And how did it work for us? I guess it boils down to you need an idea, and then you need to have a team of people who can do this, and you need to have some money to make it work and grow, right? Next. Our idea came after many years of working here at the Institute, and more specifically, we got into a EU research project called Refills, and it had a very interesting combination of companies and universities. So we had 2 universities from Italy, Uni Bremen, a robotics company, another robotics company, Intel making sensors, and DM was sort of the customer. And this was a very good research project with a lot of nice results, and we were lucky to be part of it. And actually, we at the Uni Bremen, we got into it because we wanted to do robot replenishment. We thought that was cool, to get a robot to take objects and put them into the shelves. And we were pushing for that, and in the early meetings, the customer there was saying, well, you know, that's nice, but it's very science fiction-y. Maybe we can do something first that scans the shelves. And then we said, yeah, we need to scan the shelves because we first need to know how everything looks so that we can manipulate it so it looks great. And let's just do something real quick with a robot that we have, and then they'll leave us in peace to develop the grasping and yeah. But it turns out that it worked really well. And after 1 year, we had a prototype that was very good. And at some point, the customer came to us and said, hey, you know, this is really nice. If we could buy it, we would. Okay. And then we went to Michael, and then he's like, yeah, the thing here, he was good orienting ourselves there. It's like we should apply for some funding to get started. And this takes us to the next meeting. Sorry. But before I get to the funding, then we tried to find the people who could make it happen. Then it was Georg and me. Ferenc is also here from this institute. He is doing computer vision. I was mostly doing hardware stuff, making the robots move around. Georg is leading the software and making the robot smart and be able to drive correctly. And we also got Jonas on board, who's worrying about the business aspects. And so, and Michael Betz is our mentor here. And yes, basically, it's very helpful to have somebody who can give you a hand. So to tell you, hey, is this idea actually good? You know, is it scientifically relevant? And we applied for an exist technology transfer, and as part of that, then your hosting institution gives you the framework to get up and get started, and that's what we did here. Go to the next one. Yeah, and just before that, I should mention it's a complex thing. There is a lot of legalities and things, and it's very hard to find. You're gonna try to find a team that covers as much as you can, but it's always really hard, and you cannot expect to be good at everything. So basically, you have to reach out and try to use the network that is available. And I just wanna mention here, universities usually have founding support networks, and the one of Bremen here, of the uni, is called Bridge. And they were very helpful at first at asking you all of those hard questions about, okay, is your business idea actually okay? Who's going to be your customer? Going through the motions of analyzing if this can actually be viable. And there are multiple ones in Bremen, and I would say it doesn't save you from having to know about business or studying, but at least you get a big introduction to a lot of subjects, and you can at least know how much you still have to learn, and not do the terrible mistakes that are typical sometimes when people make new companies. They will warn you about those things. Okay, next one, please.
I think one more thing that can be said about Bridge, if you ever come to this point that you want to maybe make a startup about something that you did, you get to the point with the team, right? And maybe you are short team members, or you want to meet people who would be interested. Then going to the network that the university has for people interested in starting up thingies is a great place to meet like-minded people, right? We met a lot of other startups where actually parts of the founding team, they met through something like the Bridge network in their own unis. So really, this is the place to go to meet other people who would be character-wise open to the idea.
Yeah, you have to be careful because there are some people who just want to be part of the scene and say, I'm a founder, and it's just blah, blah. but you will find some of those, and maybe some of them who actually want to do stuff, and those are the ones you want to talk to. Germany offers this funding system. It's called Exist, and they have two basic programs. One is called Business Startup Grant, and with this you can get a scholarship. You and 3 friends can get together and get funded by 18 months or 2 years. And it's not a lot of money, but it can help you get some time where you develop your business idea and not starve. And the next one is the most interesting one. It's the Research Transfer Grant. And there you basically apply with your business idea, and as a part of a department, you want to take something that you developed in a research project and try to make a company out of it. And this is what we applied with here. And yeah, it's a really cool program. Search it up online. But be aware that if you want to apply for it, it's quite a lot of preparation. The competition is fierce, and you can expect to need about 6 months to get it to the point where you have a chance. And then you go to Berlin and you have to present it in front of a lot of interesting people, and hope that they give you the thumbs up afterwards. So Ubica got funded, and that's how we got our seed funding to get started. Okay. And yeah, it was at least at the beginning the 4 of us working on this, and this is what the team looks like right now. So we have managed to grow a lot, and this is one of the hard things. It's not just the technology, but you have to find the people who can make the project happen, and establish the processes so that they can work together and make something nice. Okay, next.
Okay, that was already all the company blah blah.
All right.
We managed in 23 minutes. You
3 minutes too late.
you saved a lot of time.
Okay.
Thank you. Okay, with that, I actually want to jump into the first technological topic, and that's MLOps. That is something that we stumbled upon a bit later, actually, once we started to make things at scale software-wise. And I guess it's a term a lot of you have heard, or a lot of you have not, but it's nothing that we came up with. You can find books, there's a Wikipedia article, and well, we are attempting our own way of doing this, and I want to highlight that. But the Wikipedia kind of overview says, okay, this is something that has to do with machine learning. It's going to take some tools from DevOps, so continuous integration, continuous delivery that you have, and some data engineering. And wherever these intersect, this is what this is. So that's the drawer in your mental cupboard where this should go for now. And I want to first motivate why we are looking into this. So first of all, two pretty pictures to calm us down, or videos. Basically what our robots are doing, they are running a lot of very specialized detectors on image streams. A lot of cameras, black and white, color. And we have a network just for detecting empty facings in color pictures. Not in black and white, not in black and white from too far away, and so on. This is a very specialized detector, and you need that specialization to actually get to something that you can train such that you trust the data somewhat, but also for your engineering, of course, you have to plug these results together, and for humans in your mind, this actually helps a lot. And here we have another network, which is basically a price validator. So that's actually a combination of a machine learning thingy with a standard computer vision approach. So we basically start by taking an industrial barcode scanner that sees these barcodes that encode the product that is for which you give more info on this price label, right? Because there's text that says, Folgemilch, what you see here, right? Some meta info and a price. And the customer now wants to know whether the price is good or whether the price label has to be taken, has to be swapped. So then we have the first trained network, actually several ones, that try to recognize whether this barcode is on a price label, because the customer has these barcodes also in the environment without price labels. So you try to find in the picture, in the vicinity around this, do I detect the price label? And then there's unfortunately several types of price labels in terms of layout, in terms of font used. And then we're trying to, after we identified the type, read the price with OCR, and then we match that against the price that is given in the database of the customer. And then you can say thumbs up, thumbs down. Okay, and both of these approaches have at least a component that is based on deep learning or machine learning. So it's data driven. And of course, you want to get these things better. And the robots continuously scan, right? Every night we have this fleet, they scan, so you can every night get more data. Maybe we have a couple of students or somebody external that hand labels data. So every day we have a bigger pool of data, and you can say we can retrain to really get the last percentage of performance. So continuously training the models. It's not like we ship something and then we forget it. We want to touch it. Now here is a different problem. There's two pictures of a shelf, 2 different days. They almost look the same, but one product changed, and it's this one. So let's say until day 1, this is how the product looked. And as of day 2, Nivea decided to change the design. Subtle. You see there's all of a sudden there's blue. Here there's less distance. And if you actually read the text, part of the text changes. The bottle is also different in size. The scene here has a different angle. So the appearance has changed. Some of these changes will be subtle, so your detectors will still work. Some of these changes, they're not subtle. You have to retrain. Problem is, the products, they change, but they change without the retailers knowing it. For their own brands, they might know because they are designing it. But for everything that they buy, like Nivea, that just happens to them. It's kind of surprising. So the manufacturers, they just decide to change this, and they send a new product, right? It's not like they have an API and they're telling you in 3 months this is going to be new and everybody is prepared. No, just new and you put that. So the robots will just maybe no longer see Nivea men sensitive. And unfortunately, internal studies show that 100% of the portfolio change within 1 year. So that basically means 0.5% of the portfolio have to be retrained every day. And that's actually a reason why our business model is that we sell the software updates against the monthly license fees, because the customers want the robot to be updated every day. So they want new networks for the stuff that changed. Okay, so it's actually an ongoing process of retraining. And if you go into this, it is actually quite, you need quite some infrastructure for that. And I made a very rough overview on how this works with us. Okay, so we have on the one hand a repository of training images, right? So that is basically a Git repository where you have, let's say, some text file, maybe YAML, maybe some other database that says, that models, okay, this image, blah, 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 some name, it's training for this and this and this is detector, it's a positive, it's a negative sample, maybe the bounding box that's interesting to take out of it, so some metadata, and something that points to an external storage, because we can't put terabytes into the Git. Okay, that's the data. And then, of course, for all of these networks, we might have different parameters for learning that our computer vision engineers, they want to play with. Maybe some weight needs to be changed, typically context sensitively for particular products, maybe even. So that's in a different repository, it's also big with some text files. Now, whenever something changes here or something changes here, this is really much bigger than just 3 arrows. We have continuous integration in the cloud that gets triggered through Git hooks, which retrains the models, then runs evaluation scripts that we have determined, right, to compute based on the data that we have there, all the things that you would do as a machine learning engineer to come up with sensitivity, specificity, precision, etc., for the models that were new. The system automatically opens merge requests to another repository where we have the trained models. And then actually human developers can look at it and can say, okay, I'm going to accept that new model, we need to ship it. And then actually we have, this is also much bigger, we have another repository which is now for Debian files, because the robots, they all run on Linux, and you need more than one, because this is how we are delivering new models to the robots, which then automatically pull the updates. Okay, so that's giving you the rough idea of the infrastructure that we're having. And now I want to highlight some of the problems that we have with this, or things where we are still developing and we're trying to reduce the manual work, because all of this is work. So number one is now, let's say you shipped something and you want to know whether it works. So one thing that we're doing, we have an internal tool where the robots, after they scanned with this model that they have, randomly pick the robots certain detections for each of the models, and they upload them to yet another place with us where an internal evaluation tool looks at. And then again, manual work, can be done with students, can be done external. People sit there and they get presented with, okay, the system, in this picture, it saw here in this region, this object. Then taking the picture from the product pages, you show this, and then you ask people, hey, is this the same? Yes, no, maybe. Purely manual task, but we need to do that because you can't just fire and forget this stuff. You have to continuously run it. The cool thing about this is if the person already did a yes and no on that, and you show this maybe to 2 or 3 different people, it's kind of randomly selected from the stash that we have online, you have generated also new training data, right? So it's not only that you get statistics on how do the models perform. So at the end of this, after a week, we get a report on what are the actual values that we see from the robots in the field versus the ones that we get on our training data. And then you can basically decide whether the training data represents reality or whether we have particular models where we have problems. But at the same time, every week you generate training data where you then can decide, okay, well, let's now merge those into the training data set and train again and keep going. Okay, so that's one thing that we have set up. The second thing is now this automation. This is just a very small screenshot showing you this is how it looks then in GitLab with us. Once the system is done, Ferko Ferenc gets assigned here. This is a report. Look at this, some pretty plots down there, which I didn't screenshot. There's then links to the detailed reports, but basically you want to give people very quickly an insight to decide, okay, we're going to merge this. Because this is kind of a chore, right? Like it's every week you have to do this, or every 2 weeks, or whatever you decide, and you need to make this palatable. So that's one thing. But so far I've only talked about individual trends. The other big thing that we're working on is actually a bigger dashboard, because you want to now see how the robots behave in the field. And you want to detect, now not on the individual level, but you maybe want to see, okay, well, after we push this new set of models, performance dropped for maybe one particular robot, or for the entire fleet, or for a particular camera, because then we can figure out, okay, either the model is wrong, or actually the performance is not worse because of the model, it's because of something with this robot, it broke, this camera is bad, or it's something because of the way that particular robot drives in the store, because the others in the fleet, they don't have the problem with that network. Okay, you start getting the picture. It needs to, at the end of the day, we deploy those models on these devices, and you can no longer just look at the individual pictures and say, oh, but it works nice, because the customer wants to see that the bottom line is working. And for that, you need some sort of dashboard that gives you overviews over the entire fleet, over trends over long times. Okay. I think that was it for the ML Ops. 12 minutes, close to the goal.
Okay. This is the last section. Please bear with us. Okay, thanks, Georg. So I also want to talk a little bit about technology. This is quite graspable. It has a lot to do with hardware now. But the theme of here is like, we want to have this fleet of robots, and we want to be able to sleep at night. And so we just want them to go out and do their thing and work and scan every night, every workday, and not be a headache. And that is a trend to having long-lived robots, which is a bit different to what we would do in research here. A long experiment, it would have been, I don't know, 4 or 5 hours. But now we want to have a multitude of robots, and they have to sort of just keep doing this every night. How do we get there? Okay. As you see, hardware development is an incremental change game, where we started here when we were part of Refills. Maybe if you took the lab tour, on the second floor there is a Donbot with the big arm, and that's what we used at the beginning. Then at some point we managed to make small prototypes, and we're trying to refine which hardware do we really need to make this work. This was all proof of concepts, prototypes, and it's getting better and better. We're also changing how we build this stuff. As you see over here, we have a lot of aluminum profile. It's a very nice prototyping technique, but it doesn't scale with price, and it's a lot of manual work to put these things together. So eventually we're switching to doing things with sheet metal and having companies cut this with laser or plasma and bend it as we need it, and then we get it ready. And then found a way to make plastic covers that didn't cost a fortune. And the robot starts getting smaller and more efficient and safer. And it takes years, because often you're making these changes and you have to figure out if it was a thing in the good direction and get everything to work right. I guess the milestones here is that in 2021 we went and scanned 100 stores of this customer with a robot that looked like this. And there we had, I think, how many robots were doing this?
Oh, it was just one.
Just the one, okay. So we had this one robot that had to survive being taken apart, driven somewhere, put together, do the scan, and then again for more than 100 stores. And that was an interesting test. We thought things were going to break way more than they did, but and now we're here. We had 4 robots doing their work every night in 4 stores. And right now we're in the process of actually delivering 50 of them, which you might be able to see if you go to a DM store at night. You might be able to see a flashing light moving around. Sometimes you see it from the outside. The risk, as you see, also if you discover that you have problems in your hardware, is increasing, right? The cost of fixing some mistake is very low at the beginning, because you're only making a few. But once you figure something out here that you need to change, then it can be a quite expensive proposition. Okay, next one. And the thing that I want to get into this talk is that to get to reliable robots, this is a picture from Wikipedia about the long tail. And what I want to say here is that we have a few products that happen a lot, problems that happen a lot. Maybe some electrical thing or some connector is wrong and everything, and those tend to happen a lot. And there is not going to be that many of them, but you'll quickly see them, and then you can fix them and improve your robot. But there is also going to be the long tail here, which a bunch of problems that happen seldomly, spurious stuff. Some sensor dies, but maybe once a month, and you need to get rid of all of those problems to make a good robot. And the problem is that you would think, well, if it happens seldomly, then I don't care so much. But it turns out that there's also so many of them that at the end, the area under this curve in the long tail can be significant. So you really wanna fix those things, or they're gonna make your life hard. We ended up coupling this as, okay, you wanna discover problems in the software, and you wanna discover problems in the hardware. And it turns out that for those two in particular, you just need to have a lot of robots. They need to be scanning, they need to be doing their thing, and it's a numbers game. The more of them you have out there, then the bigger chances that you're gonna be able to see something. And the last one, it could be that you build the robots and there is a problem how you're making them, and it turns out that you also get better just by making more. Okay, the first two, you have a very experienced technician, and you're making it very carefully, and the founders are looking at every little detail, and they tend to be very good robots. But once you have to give it to people who are going to assemble them, and maybe they're not super experts at the beginning, you want to catch what is happening wrong, and that means also you have to just do it a lot. Okay, and this doing it a lot then comes with a few complications. The first one is, of course, your hardware has to be good. You don't want the wheels to fall off when the robot is driving in the night. But that's sort of obvious. One thing that is not obvious is that we ended up having to instrument the platform. So the robot has additional sensors, actuators that look inside and tell the robot about how stuff is going. So we discovered that introspection is very important. You want to measure all the voltages, all the currents. If there is some device that has some state, you want to catch it. And then you end up making electronics that are quite tailored to this particular robot. And this not only gives you more information, but it also helps you cable the robot, because we started with a robot that had a lot of cabling done by hand. And we eventually could switch to a PCB that had one connector for each device on the robot, and then the technicians cannot make a mistake. And if you manage to do it right, then you also go for different sizes such that they cannot connect it in the wrong place and things like this. And this makes your troubleshooting way better. And here we added also relays and MOSFETs such that we can turn things on and off and restart parts of the robot if we need to. Okay, so at the end, you might need more sensors and actuators than the application really needs. But we think the customer doesn't care about this stuff internally. They just want a good robot. But we realize that we need these things to make the robot reliable. Okay, and then you also need to have functional safety, because you want to have all these robots work and do things in the nights, and you don't want to be watching over each of them. So then it's very important that you develop a safety concept. And luckily there are standards for this. And this is a close-up of the bottom of our robot. We have a bumper, and this is like our last defense if the robot just goes crazy and would crash against something, ignoring all the other sensors. This will stop the robot and he cannot drive any further. This over here is a safety-rated laser scanner, such that we can also say, okay, if anything comes too close to the front, then please stop the robot, and the robot won't move anymore. Of course, you need an emergency stop so that a person can turn the robot off if they need to, and everything has to be connected to safe motor controllers. So you have to, this concept has to introduce like all the parts of the robot, and basically you want to be able to trust this machine to not burn your house down. So it should consider everything that can typically go wrong and just go back to some safe states if anything is weird.
Is it okay if I inject one thought?
Yeah, please.
So just to make it explicit, right? You said in the beginning we want to catch these seldom errors. So that means we have to get a lot of hours of the robots doing stuff. That means we have to get the robot to a state where it does stuff without us watching, and have a lot of fleet and have days and days of operation. That's why Alexa said, here, before in the prototype phase, we would just run 4 hours and watch it ourselves, but that doesn't scale, right? So you need to get the machine such that it can work ideally for weeks without you looking at it to then hit on the error. That's why he's talking about the safety, and you want to trust it not burning the house down.
Yeah, and next one. Yeah, and the last piece of the puzzle here is that to be able to do these experiments without you being there all the time, we had to go from a robot that you had to plug in to something that just has a base station and he charges himself autonomously. And yeah, we were surprised of how big of a difference this made. We really did not appreciate at the beginning how cool this thing was going to be, but this is a picture of our training area. And now the robot, we have some shelves, and we have a system to do inductive charging. And basically the robot can come in here, charge, drive out, scan the shelves, do some tests there for a few minutes, come back, charge again, and you can do this hundreds of times on the weekend. And the first time that we were trying to tune this parking procedure, we were not sure if it was going to be okay, but then at the moment we realized, wait, we can just let it simulate 1 year worth of dockings and undockings over the course of 2 or 3 days. And that's what we did. And then we had a good feeling that the system was going to work out there, just because we had so many repetitions and it was working well. Okay, so yeah, being able to be autonomous, this independence was a really cool thing. Next one. And this brings us to, all right, and now we have all these robots out there, and they can work, and nobody has to look at them, but you still want to catch when something went wrong. And this is where the concept of ease, of storing memories, and becomes very important. Here we have an example of a logging of a robot, and this is a full day of scanning, and then another and another. So at least 3 days here where the robot was continuously working, and you can see here that the sensors had some short warnings that those are yellow. Everything was in green. If there was any error detected, then there was a red marker. And this type of logging can give you the opportunity to find interesting areas, and then you can go look at the specifics and see what the hell was happening. And this graph over here is an example of a docking test. So these two lines are just voltage and current. So our robot was driving to the docking station, charging for a few moments, driving out, doing something, coming back, charging, and those are all these up and downs that you see here on the current and the voltage. And then eventually it came back, and now it's just charging. But here it's also 1, 2, 3, 4, 5 days, and I cut it. So we can do very long tests, and yeah, catch these little problems before it's too late. Okay, I think that was my last one, right?
Mm-hmm. Okay, then let's jump to the last. Thank you, first of all, for your attention. We actually sped so that we have time for questions now, but of course we also have to say, hey, we're hiring. So if anybody wants to start working for us, go to our website, ubicarobotics.eu. We have job pages. They're not all in production, all the jobs. There's more below. Development, yeah, both hardware, software, not only computer vision, also navigation, but yeah, also cloud services, infrastructure, all of this. So yeah, if you or some friends of yours or some students that are really good, that just finished and they're looking for a job outside of academia, maybe you can recommend us. And then yeah, now we have more than 10 minutes to actually go on the details.
So, Michael is coming.
I just want to add here, so yeah, so if you want to have an interesting job there, you have to join there, right? But if you want to fund your company on your own with interesting ideas, you have to stay at university, right?
Thank you for reminding. Okay. Yeah, thanks for the interesting insight. In the slides with the NVIDIA chain, with the Nivea change from the Rasiergel to Rasierschaum, you said that it's hard to recognize or impossible to recognize it, but isn't the price tag the same?
Yes.
I mean, can you just heavily rely on having price tags? Because I've never seen a store without price tags.
Yes, so we actually had, that's a one development that we had, actually with the student here, also with Michael. trying to generate training data based on the price labels. A couple of small details there that come in. So the problem there is you can generate a lot of data based on that, right? Like if you find this, maybe those separators, not all the customers have them. Maybe you know, once you read that type, the dimensions of roughly of the product, because they know this for logistics planning. You can cut out, totally valid. Problems that we had is number one, what if there are actually misplaced products, right? So you have to weed out the wrong data. And for the network, right, we're just right now verifying that the product on top of the price label, that they match together.
Ah, okay.
Right? So that's the approach that we're taking. Because recognition just on its own turned out to be too hard. So if the product changed too much, then your verification will fail. So that's actually what you will notice in the software, that all of a sudden you say, this is not the same. And that can be because they switched appearance or because somebody put the wrong object. So it's not a silver bullet, right? You cannot completely automate the problem. And actually, the second problem is the customers want this a bit more detailed. So for instance, for DM, they here encode a number that is, it's a bit meta, I would say. So it's the number that they give forever to Nivea sensitive foam at 200 milliliters. But there is another number which describes this particular shape and appearance of this product. So let's say Nivea makes this product over 4 years and they have 4 different instances of the bottle. Then this meta number is always the same, but they have 4 different numbers for the appearances. The moment this thing no longer has 250 milliliters or they're changing the recipe inside, they're giving a new meta number, right? But let's say they do this legally because they're supposed to inform you, especially for the online stores, exactly what you're buying as a customer. So the problem now is for us, we need to track models for the second type, right? Because they want to actually also know what is the appearance that we have on the stores. So DM, here's the problem, they just give you the meta number, so even if they change the price label, just based on the label, you will not know that this should be a new model. Rewe, for instance, they swap this here to give you the second number on the label. So then based on the label, you can already realize, okay, we have to retrain because they put something that we have not in the repositories. Yes, so I went on a tangent here. Basically, yes, we have something like this, and you can generate training data based on the labels, but then still people have to look at them. But you can generate candidates.
Can I make a small comment to that? I guess that the thing that makes us very hard is that at first we thought, what recognition rate do you need? Maybe 80% is fine, or 90%. But it turns out that we're being confronted with customers who want really high rates. So they're not happy to have a few percents wrong. The data has to be quite right. And this leads to us specializing the detectors and trying to get the performance. And those last percentages are always really hard and make you have to tweak a lot.
Yeah. Okay, thanks.
Okay, thank you, Georg and Alexis, also for the talk. I wish I could also have like a Ferenc with you. Just extend my greetings to Ferenc. So the questions just asked by Tom. So I mean, a question related to what he asked is, perception is a complex problem, right? And my point is, you can't just perceive from sensors, so that sensors are not kind of enough for perceptions. So the point here, for example, is what is it to be a product? What is it to be a milk? Is it just a problem of bottle? Because if you put a human being in the store or in one of those supermarkets, no matter how the product change, the shape, the color, and so on, the human will still recognize that this is a milk. And because he has a huge knowledge about what milk is, and to achieve the point, it has to extract all those knowledge somehow and conclude that, okay, this is so I don't want to provide you with any answer because this is also my topics of research and suggest just to that perception is somehow complex. For example, imagine that you are only doing these perceptions based on kinds of scanning and looking at appearance. It changes a lot, right? And the consequence is you will end up with kinds of data set with huge entropy, with the network kinds of confused and so on. So somehow you can't just perceive, I mean, from sense of it's a difficult problem.
Let me try to phrase what resonated with me from that, or what I can mirror. So number one, I think what needs to be understood about our product, if we go to the very beginning, if you look at the vision here, that this is a robot that cannot do things, right? So it does not have a manipulator. So all of the branches of perception that deal with affordances are kind of lost on this device, right? It's not looking to grasp. It's not looking to push anything or so, right? At DM, they don't call this a robot. They call this Filialsensor, which is, I thought it was cute. It was an internal communication HR spin, but it's true. It is actually just a measurement device. And also, if you look at this, I said, well, they don't know anything about the store internally. This technology is for them just the first kick against this problem of removing a blind spot. Of course, we're trying to make this as good as possible, but it's not clear that this sensor on its own will forever remove all of the perception problems that they have, right? It can be that you have to support this with shelf cameras, with other cameras, right? But yeah, the first point is we don't go into affordances, we just want to see the stuff that there is. The second point is this empty facing, whatever detection is already one of the more high-level things we do. I said in the beginning, hey, we're just looking also at shelves and where price labels are. Turns out some of our customers, they just want that. They want a moving barcode scanner. And that thing on its own can already pay for itself if the store is big enough. So if you're thinking really huge stores, they don't want any intelligent. They want something stupid that goes through and does beep. And then, but beep with AA was here when I made beep. So we're not looking into these metaphysical things. But on the way to getting the moving barcode scanners, you get to find actually some interesting problems then maybe in the hardware development, in the navigation. Yes, basically that's what I wanted to clarify around
also
that.
for the progress.
Thank you. If I might add something small, I think part of the approach, and I think it kind of shows in this picture, is that we're not trying to solve the really hard perception problems. We're trying to exploit the structure a lot. This came from discussions here at the department, where we said, hey, the general perception problem is just too hard. But luckily, the stores tend to have a lot of structure that we can use. And for example, the shelves, they all get made by almost by the same manufacturer, and they have a specific shape and form which we can use to recognize them. So we can take shortcuts and look at a smaller problem to make it possible.
Actually, I just realized we forgot something. It's good that you asked this question. We have to do this for the future. Some people ask, what does Ubica actually stand for? And the two of us, we cooked up this name because it's Spanish and Italian, and it means he or she or it localizes, as in, tells you where something is. It doesn't mean he understands or he interprets or anything like that, right? The initial ambition was, this is a device that tells you where things are in an environment, and that's what we're trying to solve.
One last question.
Yeah, actually, I have two questions.
Okay. I'll start with the easy one. So when looking at the of your logging you have, so it was kind of more numerical data. So we have the currents, or we have the measured voltages of the charging and so on. But do you also store the big data? So for example, the images somewhere, and do you link the images, for example, to the state the system was? For example, it was charging, or it was here and there. Do you also store that? Because that would be kind of huge data.
Mm-hmm. Yes. So basically, this is really just the hardware diagnostics, which is a reasonable abstraction. Yes, we do store the images on the robots for a certain amount of time for revisiting. But for fixing these problems, getting all of the data is much too big. One thing that we actually copied from another company that recommended to us, from Magazzino, from Moritz, it's a really good idea, which goes a bit beyond that, is to have accident recordings. So the idea is there is a system running that is recording in a short buffer all the images, everything, like the full Monty, but it's throwing it away. It's a running buffer of 2 minutes. And anytime something really on the high level that is classified as an accident happens, we write that separately, and we push this out for human consumption. And that was actually a very good idea, because then for 1 or 2 minutes, the data is small enough that you can upload it. One of our main problems is actually that a lot of these stores have bad internet. So you really can't count on big bandwidth. But like this idea, that makes a lot of sense. And then you might come in with a navigation engineer having a question of, hey, why did this guy run into the wall, right? Or why did he not dock? Or I don't know, why did the safety trigger? And then that person wants to have all the images, wants to have all the laser, wants to have the internal state of the cost maps of everything. But it's horrendously expensive to save all of that for everything. So that idea of that buffer, that was actually pretty good. And then you have this illusion of always having all the data when you need it, right? But you actually just only have it when there was an event that you wanted.
Mm-hmm. Okay, yeah, we have kind of the same. So whenever there's a keyframe which is important for the robot, then we store all the information and we discard in between eventually. And the second question, I make it quick. So I know that there are also other approaches where you have RFID tags in the shelves. So there is no need for having a robot, a camera. You have digital displays, so there is no need for the image recognition. Do you think that the store in the future will more look like this? So we have specialized shelves and specialized displays, or do you think that in the future there's the need for having a robot driving around and so on?
Mm-hmm. Yeah, that's a bit what I said on the competition slide, right? It's actually 2 questions that you have there. Number 1 is about installing technology into the shelves for sensing, for making the problem easier. That is actually a very valid approach. But, as I said, the bigger the store is, the bigger the investment for this is, right? And we're actually talking a lot of money. So if you just multiply this out through Rewe, through Kaufland, through Lidl, you get into, let's say 10-20% of the net worth of that company for cameras and cabling and server racks. So that's a huge proposition. So either smartphone cameras get like an order of magnitude cheaper, which would be hard, or it's going to be difficult to have this for everything. And we, as a society, right, we're moving for sustainability. We're looking into a time of crisis. Do we actually get all the resources? I'm not sure whether we can equip so many stores with so many sensors. Like just the numbers game is huge, but for some stores that can be possible, right? Like there's this trend, micro stores 24/7 fully automated in rural areas, Saxony, Thüringen, there are some like that. That can make a lot of sense if you have a Tante Emma store, 20 shelves, nobody ever goes there except to put products. Yes, there it totally makes sense and our robot will not compete. RFID is a totally different thing. Competing company, Metra Labs, is really good in RFID-based scanning robots. Problem there is, not problem, they focus on stores selling clothes. And RFID has two problems. Number one, you do not get a good spatial accuracy on one scan. You have to pass several times because one time it will say, I'm here, and then the tag is here, and you really have to, average that out. And the second problem is the more tags you have in a particular volume, the bigger the interference will be between those. So for, cubic meter with 50 jackets, that works. A cubic meter of DM with 10,000 little sprays or lipsticks, this will not work. Your antenna on the robot cannot emit such a strong field to get all of them to resonate and answer back and still get meaningful data. So there's a technical barrier on how dense these things can be. So it's not the silver bullet for all inventory tasks. Otherwise, we would have gone there. Michael maybe remembers in the first meeting at Refills, that was the question, like 8 years ago. Why did we actually go with cameras for this in the EU project? And then they quickly said, no, doesn't work for these type of shells.
But I just want to say, we were shocked that the robot would be the economical thing. We thought, cameras are going to be cheaper. And then it turns out that you just need so many. And then the quality, they need to be sort of good. And then it just adds up. And then having these cameras on wheels starts to make economic sense.
Okay, thank you very much.